We left off last class on this slide here. The gluconeogenesis pathway, when there's an accumulation of lactate, is a way for us to have glucose be produced as a result of this increasing concentration of lactate. And it's a way to address that, because if you can imagine, lactate, when protonated, becomes lactic acid. So we don't want this buildup of acidic byproduct, but rather can now be used to produce more glucose and create more ATP as a result. But what's important to note is that glycolysis and gluconeogenesis share a lot of the same steps. And what's important to note is that the steps along the glycolysis pathway or gluconeogenesis pathway, what can end up happening is that the reactions can run forward or backward or reverse, all depending on the concentration of the reactant versus the product, or the substrate versus the product. So if there's an increasing concentration of product, what can end up happening is that this process is able to be run in reverse. But there are some steps that are irreversible that kind of serves as gateways, or ensuring that that once you cross these steps, they can't go in reverse, whether we're dealing with glycolysis or gluconeogenesis here. And the two of them lie at the top of the glycolysis pathway, and one is at the bottom. The first lies at the action of hexokinase here. And if you take note here that each of the irreversible steps are associated with either the consumption of an ATP or the production of it. And so the first irreversible step is the production of the product of glucose 6-phosphate by hexokinase. And so once you cross that step, it's irreversible. You can go back and forth fairly easily between glucose 6-phosphate or fructose 6-phosphate, depending on the concentration of the product, or the substrate or the product. And the next irreversible step is at the level of action by phosphofructokinase. And so for both hexokinase and phosphofructokinase, once these phosphate groups have been added to their substrate to produce their product here, it's an irreversible step. But on the gluconeogenesis side, what ends up happening is that there are phosphatases here that are removing those phosphate groups. That's what phosphatases do. They're an enzyme that remove phosphate groups. And so that's the means by which, on the gluconeogenesis side, those irreversible steps are overcome. But in glycolysis, after the action of hexokinase or after the action of phosphofructokinase, you can't move backwards. And throughout the steps between phosphofructokinase and pyruvate kinase, these again can either move forward or in reverse, depending on the concentration of the products. But the next and last irreversible step here is at the level of pyruvate kinase, with the production of the ATP here. What ends up happening for gluconeogenesis is that this irreversible step is overcome in two waves by carboxylase and our carboxykinase, where the first action produces oxaloacetate, which is something we'll come back to in another pathway we'll address soon. And then after that, there's a carboxykinase that produces the phosphoenol pyruvate that precedes pyruvate. So the main takeaway here is that there are some steps that are irreversible that have other actors on the side of gluconeogenesis to overcome those irreversible steps, but largely between those irreversible steps, things can move forward or in reverse, depending on the concentration of the product. Now, when we have high concentrations of glucose that are being produced, and if they're not being used, there needs to be a way for that glucose to be stored. And the way in which excess glucose is stored is in the form of glycogen. Glycogen is a polymer, a macromolecular polymer that helps store unused glucose as a way of, for lack of a better phrase, potential energy that is stored within our liver and in our muscles. What ends up happening is that once glucose 6-phosphate is produced by hexokinase, there's a mutase that will basically shuffle around that phosphate group over from the 6 carbon to the 1 carbon, making glucose 1-phosphate. And with glucose 1-phosphate, it'll interact with a molecule called UTP, uridine triphosphate. And there's an enzyme that will promote the interaction between glucose 1-phosphate and UTP to form UDP glucose. There will be 2 phosphate groups released, and it'll produce this combination of glucose with uridine diphosphate, UDP. And then what ends up happening there is that this is the substrate for another enzyme called glycogen synthase. As the name implies, it is an enzyme that helps with the addition or the synthesis of another glycogen monomer to a growing polymer. And so via glycogen synthase, glucose can be added onto the growing glycogen polymer, and there's a UDP molecule that is also part of the product there. And so this reaction is the way in which excess glucose can be stored as a reservoir of energy within our muscles and within the liver. Now, when there is a need for glycogen to be used, the way in which it's called upon, for lack of a better phrase, is via an enzyme called glycogen phosphorylase. What this enzyme does is that it'll add a phosphate group to one of these glucose units within the glycogen polymer. And so what will end up happening is glycogen phosphorylase will add a phosphate group, producing a product of glucose 1-phosphate, and it'll leave the glycogen polymer with 1 less glucose monomer. And this glucose 1-phosphate will be converted by mutase to glucose 6-phosphate, which is the molecule, the second step of glycolysis. And so it'll be prepared to re-enter back into the glycolysis pathway and be used to synthesize more ATP. And so we talked about how the glycolysis pathway has these irreversible steps that once you cross them, they're irreversible. But what's also important to note is that there's a degree of regulation and feedback that helps to control this pathway in addition to these irreversible steps. And as you can imagine, the level of the regulation on this pathway involves those irreversible steps. The first feedback loop that we see here is that the enzyme hexokinase is regulated by the product of its reaction, glucose 6-phosphate. Once glucose 6-phosphate is produced to a certain degree, it'll start negatively regulating hexokinase's activity, providing a negative feedback. And so this is helping to shut off the enzymatic activity of hexokinase once there's enough of the product of that reaction. Another level of feedback here is at the level of phosphofructokinase, and it's regulated and inhibited by ATP concentration. As more ATP is being produced by the glycolysis pathway, for lack of a better phrase, once there begins to be enough ATP produced, it'll feed back and inhibit or negatively regulate phosphofructokinase. And so these first 2 examples are instances of negative feedback where it, by means of its interaction with the enzyme, it's able to inhibit and slow down the enzymatic reactions. The last level of regulation is at the level of pyruvate kinase. What ends up happening here is that it's acted on by something above at the level of fructose 1,6-phosphate. As fructose 1,6-phosphate is being produced, it's going to feed forward and positively regulate pyruvate kinase as a way of, for lack of a better way of putting it, it's a way of communicating to the enzyme to get ready to promote the enzymatic reaction for which it's meant at the level of phosphoenolpyruvate. And so as fructose 1,6-phosphate is being produced, it'll act on pyruvate kinase and promote its activity, feed forward positive regulation for the downstream enzymatic activity that pyruvate kinase acts on, producing the ATP down here. And so these are examples where there's a level of regulation within the glycolysis pathway to inform how these enzymes should be regulated and be acting. That'll wrap up this glycolysis lecture, and I'll see you all for the oxidative phosphorylase lecture.